senior scientist there. My name is Georgios Kokinis. And today, on a bit of a different note from most of the inputs from the industry, I will be presenting our work on a TinyML implementation for a textile-integrated breath rate sensor, a bit from an academic point of view. Some words about Silicon Austria Labs. Is a research institute, publicly funded, based in Austria, in 3 cities in Austria, and is focusing its research on all kinds of electronics-based systems, from power electronics to embedded systems, system integration technologies, RF systems, and sensor systems. My team is electronic sensors, and we are conducting research on sensor elements, but also readout systems for sensor nodes. Thus, naturally, we get into the realm of edge AI, and recently started working on the field. Since I'm going to be discussing textile-integrated electronics, some driving factors behind this niche of electronics. One is the miniaturization driving factor. Since traditional transistors, we have come a long way to grain size MCUs. And on the other hand, we have the other main driving factor, which is additive manufacture, which also incorporated in our project with multi-material 3D printing. Of course, we cannot forget about market potential and societal benefits. The last years, there are all kinds of new usages of e-textiles in diverse applications, from safety features, heating, health monitoring, rehab, fitness, and every now and then you have a lot of new applications popping up. Of course, you can already purchase, and there's a lot of products in the market that are really highly advanced, but academia still spearheading the field. And here is an example of an embroidered capacitive EMG sensor from Fraunhofer, and a laminated textile-integrated capacitive EMG sensor from TU Berlin. In the context of flexible, of textile-integrated electronics, flexible interconnects is a holy grail. Most of the solutions we find in academia and in industry is basically consisting of dielectric islands where the circuits have been assembled, and then there is a search for interconnecting technologies that could deem these systems viable and robust. But what is the need for textile-integrated electronics and sensor in healthcare? Of course, you are aware of the aging of population, especially in Europe, and the substantial burden it poses on the social healthcare systems. So is there a way through adaptation of such systems to reduce the hospitalization days in hospitals? To these burdening issues, our project textile-integrated hybrid printed electronics comes to bring some solutions to answer some questions. On the one hand, by remote patient monitoring systems, where alerts can be provided to healthcare professionals about a deterioration in the health of a patient, and on the other hand, to provide a seamless integration system for electronics and sensors into garments. So our approach to the issue is similar to other systems that are in an academic mainly field. So is to have a 3D printed multi-layer dielectric island where the assembly of the circuit comes later on, and then use in our switch back some embroidered interconnects with a swing machine, but also to develop embroidered breath rate sensing elements. So we came to develop the textile belt. We have all these kinds of modules, the power module and 3D printed LED, a heart rate sensor based on a PPG sensor module, an MCU and accelerometer, and finally a breath rate sensor. And here you see an early prototype of the system. I'm focusing here on the breath rate sensor. We have the different layers of the dielectric island upon which was already 3D printed, upon which conductive ink was also dispensed. And we used an embroidered carbonized silicon yarn to basically form a strain gauge that is measuring the expansion of the chest. So we developed this sensor module with the MCU, and then we had to decide what we're going to do with it. The first obvious solution is to use some peak detection algorithm, but then we came with really big hurdles because such sensors have a burn-in effect, but also there is a lot of offsets appearing at random points during operation that also the peak detection algorithm cannot tackle. Thus, the obvious solution it was to look into an edge AI implementation. First of all, we screened for public datasets. Unfortunately, most of them used ECG and PPG data that were then labeled using impedance monography or capnography, and we only found one data set that it was using a sensor similar to our system. Unfortunately, that one as well had several limitations, which I will touch on the next slides. So we opted to create our own custom data set. 5 volunteers were recording data in a seated or in static position, and of course we took care of anonymity in the labeling. Going back to the WOG dataset, main hurdle was that it was actually missing labels. So ironically, we used the peak detection algorithm to label the data on ourselves. Here you see a nice example of how this worked perfectly well, but then we had data that looked like this, and actually it was not very easily usable. Here you also have an image of the raw signal and the spectrum. So we gathered our data. We went through a data preprocessing pipeline where we cleaned, filter with a bandpass filter of 0.1 to 1 hertz. This is the region that is of interest. We segmented it into 3-second splits, normalized them, and labeled them via an event push button. That was also a pretty good strategy, as we could have a very well-defined birth rate on our data. Moving on to the model architecture, here we heavily depended on edge impulse and the neural architecture search feature via the EON tuner. There was an automated process to find the optimal neural network architecture design. We narrowed down our search to two distinct models. One used a convolutional neural network, where the input was the raw signal with some pre-processing steps on the MCU. And the second was a deep neural network with a wavelet transformation. Naturally, the CNN net model had many more parameters than the DNN and we proceed on training both on both datasets, and we had a really good convergence. And in the metrics, there was obvious that the TextHype dataset was performing slightly better, and the CNN model was performing always better than the DNN. This followed the model deployment. We use an STM32L4 microcontroller, some initial pre-buffering, pre-processing steps to provide the data for the CNN network and the DNN network. We acquired the data through an analog to digital converter via DMA, and we used two timers, one to precise control the sampling intervals, and the second just as a solution to measure the intervals on the inference time. The pre-processing on the MCU consists of a FIR filter from the CMSIS DSP library, some buffering and event flag, and finally some minimum and maximum normalization. The post-training optimization significantly reduced the size of the models by a threefold, and here I included an image of the filtered data from the sensor. Finally, we run the inference at the edge. For the convolutional network, we had a relatively large inference time, close to 6 seconds. But also, as we've seen before, the results were much better. And we have a power consumption between 3.3 to 6.6 milliwatt. While from the DNN, that was the maximum in power consumption. On the other hand, was much faster in the inference time. Now, we had two datasets, and we wanted to try the public dataset that was trained from sensor data from a different sensor to see how well it generalizes on the sensor data from our model. Unfortunately, we see that the model does not generalize very well. We have a mean average error of 8.3 for the CNN and the 10 for the DNN. So the next step would be to fine-tune the model with the data from the TextHype dataset and see if we can improve the performance. On the other hand, of course, the dataset that was used to train the model and was getting input from the same sensor perform much more better. So the next step is to use to further collect data and train AI models towards the remote patient monitoring system that I mentioned in the beginning. Currently, we are focusing on hydration prediction, and finally, of course, use some embedded AI integration of such a system. So that brings me to the end of my presentation. Thank you very much for your attention.